So next, we are ready to start your topic, that is your dimensions and dimensional analysis. Let's start first with what is a dimension. Now any physical quantity that we talk about can be defined or can be raised to powers of the fundamental quantities like your mass, length and time or so on, such that it represents the type of physical quantity that we are talking about. And that is what is known as dimensions for us. Now the definition may not be clear for you, but in simple terms, the fundamental quantity that we have taken, like your mass, length and time, we can say that mass is a dimension, length is a dimension for us, and even time is a dimension for us, such that we represent it by m with square brackets, then L with square brackets, and T again with square brackets. So we call it mass dimension, length dimension and time dimension. Now suppose we have a physical quantity like your speed, which is defined as distance by time. Then we can have this speed have a dimension, taking the dimension from distance divided by dimension of time. Now distance, as we know, is nothing but measurement of length. So we write distance dimension is nothing but the dimension of length, and the time dimension is nothing but the dimension of t. So there you have the dimension of time, and we have expressed speed using the dimensions for your distance and time. So we have speed dimension, which we represent by square brackets, equal to dimension of length and t inverse, that is your length per unit time. Now this can be done for any physical quantity that we can talk about. So you'll come up with different dimensions of different physical quantities by using the dimensions of mass, length and time. To tell you, dimensions basically represents type of physical quantity that we are talking about. If two physical quantities x and y, they have same dimensions, we can say that they are of same type of quantity that we are talking about. Let's look into one by one the different quantities for which we can talk about dimensions. Let's start with your distance, length, breadth, height, width or thickness. All of them is a measurement of length, we can say. So all of them, they have a dimension of L, capital L. If you look at SI unit of all of them, it is going to be meters. In CGS system, if we use, it is centimeters. CGS, if you remember, is a system where you use centimeters as the length unit, gram as the mass unit, and seconds as the time unit. Then we have area of a rectangle or a square or a circle, whose units we know is meter square in SI system and centimeter square in CGS system. Now area has a dimension of length square. It is because suppose we are calculating the area of a rectangle, it has length and breadth. So the area formula will be length times breadth. So the dimension of area is going to be dimension of length times the dimension of breadth. So I'm going to write dimension of length is simply length measurement. Even your dimension of breadth is simply your length measurement. So both of them together is going to give you L square. That's why we have L square as the dimension of area, and that is true even if you take a square or a circle or any two-dimensional figure where you can calculate the area and get the dimension as L square. Now you can check a relation between the dimension and the SI unit. The dimension of area is L square, that is length square, and in SI system the length is measured in meters, so we have meter square as the SI unit. So suppose if I tell you that dimension is ml of any physical quantity, then m represents mass, L represents length, then the SI system, the units is going to be surely kg meters, because mass is measured in kg in SI system and L is measured in, length is measured in meters. So you can see if we know the dimensions, we can predict the SI unit or even your CGS unit. One more thing, just now you saw that area of a circle or square or rectangle or any shape, we know they have same dimensions. In other words, we can even add them, like this area of a triangle can be added with this area of a rectangle, or can be added with the area of a square, or can be added with the area of a circle or semicircle, because all of them are going to have same dimensions and same units, and so they can be added up. But suppose if we have two quantities x and y, such that the dimension of x is not the same as dimension of y, then we cannot have an equation where we can add x and y. That means two quantities with different dimensions cannot be added or subtracted because they are not going to have same dimensions. That means they are not same type of quantity and they will never have same units, and that's why we cannot add them or subtract them. However, even if they have different dimensions, we can multiply them or divide them. Now similarly, when we check the dimension of volume of a cube, sphere, cube or a cylinder, for a cube the volume formula will be side cube. For a cuboid, you know volume is length into breadth into height. For a cylinder, pi r square h is the volume. In every case, if you notice, A represents your side, so we have side cube. That means dimension is going to have length cube because side is nothing but length. This L is length dimension, breadth is length dimension, even your height is length dimension. So your volume of your cuboid is also going to have L cube as the dimension. So all the volume that we can talk about is going to have a dimension of L cube. And of course, you know the SI unit is going to be meter cube or CGS unit will be centimeter cube. Then we have your density, which sometimes we even write mass density, is defined as the ratio of mass to the volume, such that mass is measured in kilograms in SI system and volume is measured in meter cube. So we have kg meter cube per meter cube as the SI unit. So you can even see the dimension of density will be equal to dimension of mass divided by dimension of volume. Dimension of mass is m, dimension of volume is L cube. We have m L to the power minus 3 as the dimension of your density. This sometimes can even be written as ml minus 3 t to the power 0. That means we don't have to measure time to know the density of any object. Next we have speed, as I've already discussed. Formula is distance by time. So the units is going to be meters per second because distance is measured in meters, time in seconds. In CGS system is going to be centimeter per second. The dimension of speed, now we are writing square brackets, so you can see we are talking about dimension of speed, not the value. So dimension of speed will be because of dimension of some distance divided by dimension of time. Dimension of distance is L, dimension of t is t, so we write L t inverse. Then we have velocity, which is defined as displacement by time. It's a vector quantity. Meters per second is the unit, centimeter per second in CGS system. Then we have the dimension of velocity should be given by dimension of displacement by dimension of time. So we have L by t, which we write Lt minus 1. Then we have a very important quantity when we study mechanics or kinematics, that is about motion. That quantity is your momentum, represented by symbol P, defined as the product of mass of the object and velocity of the object. That means if a body has certain mass and is moving with certain velocity, then we can say that this body has certain momentum in the direction of its motion given by the product of its mass and velocity. Now, unit of mass is kg, unit of velocity is meters per second. So we have this whole unit, which is your kg meters per second, as a unit of momentum. In CGS system, we are going to have gram centimeter second inverse. So the dimension of momentum should be given by dimension of your mass times the dimension of your velocity, and dimension of mass we know is m, dimension of velocity is Lt minus 1, so we get our dimension of momentum as ml t minus 1. Next we have acceleration, which you have learned in earlier classes, defined as rate of change of velocity by time. Now change of velocity simply means final velocity minus initial velocity by time. Now velocity, this v and this u, both are velocities, so they have dimensions of Lt minus 1 and are measured in meters minus 1. Then we have divided by time, so we are going to divide by seconds again. That's why we have a unit of meters per second square or centimeter per second square. The dimension of acceleration is going to be dimension of velocity or change of velocity by dimension of time. Change of velocity, as you know, is measured in velocity dimensions only. So we have Lt minus 1 divided by the time dimensions t. So we get Lt minus 1, this t goes up here with a power 1, it becomes power minus 1. So we have Lt minus 2. So looking at the dimension of acceleration also, you can guess the unit. It must be meters per second square. Then we have next again a very important quantity, which you know is your force, defined as the product of mass and acceleration. So mass, as you know, in SI system is measured in kgs. Acceleration is measured in meters per second square that you've seen just now. This whole thing in SI system we call it newtons. So instead of writing 1 kg meter per second square, we can also call it as 1 newtons. Then we have in CGS system where you use grams in place of kilograms. Then we have centimeters in place of meters. If I'm using grams centimeter per second square, we are going to call it dynes. So instead of calling 1 gram centimeter per second square, we're simply going to call it 1 dynes. Now the dimension of force should be equal to dimension of mass times dimension of acceleration. Now you have seen dimension of mass is m, so I'm writing m. Dimension of acceleration is LT minus 2, so we are writing LT minus 2. So dimension of force is going to be MLT minus 2. Next again we have energy that we often talk about, and the energy can be of any form or type such that kinetic energy or potential energy. If I'm talking about kinetic energy, you must have seen or come across the formula which is half mv square, where m is the mass and v is velocity. If you're talking about potential energy, that is your gravitational potential energy, we may have mgh, mass, acceleration due to gravity and height, such that the unit is simply your kg because you have mass m. Now to get the SI unit of energy, you can use any one formula, either this or this. Let's use this first. In potential energy, m is mass. Mass is measured in kilograms, so we have kg. G represents acceleration due to gravity, so we have meters per second square. And finally h represents height, so we have meters. When I write this again, it's going to look like kg meter square, because meters and meters they multiply. Then we have per second square. This kg meter square per second square is also known as joules for us, and that is the SI unit of energy. Then suppose even if we use half mv square as the formula for kinetic energy, half doesn't have a unit, it's simply a number. M has a unit of kilograms in SI system. Then we have velocity, which is your meters per second, but we have a square here, so we must square here, and then we get kg meter square per second square. This is again, you can see, is same, and it does not matter whether we use this formula or this formula to calculate SI unit of energy. And this SI unit of energy that we get, that is your kg meter square per second square, is what is known as joules for us. If we do the same thing in your CGS system, in place of kilograms kg, we are going to have grams. In place of meter square, we are going to have centimeter square. In place of second minus 2, we are going to have second minus 2. In CGS and SI, both have same seconds as the time unit. This what is known as ergs for us. That means 1 gram centimeter square second minus 2 is what is known as 1 erg for us. And 1 kilogram meter square second minus 2 is known as 1 joules for us. Just to tell you, your CGS system is a smaller unit system and your SI system is a bigger unit system. At this point, just to recall, if I'm talking about 1 newtons, I'm talking about force. That is your mass times acceleration. So it is mass times acceleration is meters per second square. In CGS system, we call it dynes. And your 1 dyne is simply your kg, sorry, no kg but grams centimeter per second square. So you need to remember what is 1 newtons, what is 1 dynes, what is 1 ergs, and what is 1 joules. And very soon you're going to see a relation between them because they are 2 different units in 2 different systems, so they must be related. Since your kg is related to your grams, meters related to centimeter, your newton will also be related to your dynes, and same thing with your ergs and joules. Moving on. Now one point, just now you saw, whether it is kinetic energy or potential energy, the dimension of kinetic energy is same as the dimension of potential energy. It also means that they're same type of quantity and there's no problem in adding a kinetic energy with a potential energy. Next we have work, which you might have seen is defined as the product of force and displacement. Now force is measured in newtons, displacement is measured in meters, so we have Newton meter as the unit of force or SI unit of force. Can also be written, now Newton can also be written as kg meters minus 2, and if displacement is written as meters, so when we write this we can also have kg meter square second minus 2. that we have already seen is written as joules. That means the SI unit of work is nothing but that of equal to joules, just like your energy. That means the unit of energy is same as unit of work. Also, since the units are same, doesn't matter whether it's CGS or SI, unit in CGS also will be same. That means we can measure your work done in ergs as well. Now to talk about dimensions, dimension of force, dimension of displacement when multiplied should give you dimension of work. Dimension of force is ml t minus 2, dimension of displacement is length, so we have ml square t minus 2. So you can see again, dimension of energy, work are same. That means if I have work, I can add or subtract with energy because they have same dimension and they will represent some same type of quantity. For example, you must have noticed if you have 10 joules of energy, it also means you can do a work of 10 joules. So you see we are talking about work and energy and they can be thought of same type of quantities. That's why they have same dimensions and they have same units. Next we have something called moment of force, which you will learn later in your other unit, which is also known as torque. This is sometimes can also be thought of as rotational force. Now torque is defined as some force times some distance that we call it perpendicular distance. So the unit of torque will be equal to Newton meter, because force is measured in newtons and distance measured in meters. Then we have the dimension of torque will be equal to dimension of force times the dimension of perpendicular distance. Again you can see force is ml t minus 2 and perpendicular distance L, so we get torque dimension is equal to ml square t minus 2. You can again see the dimension of torque is same as dimension of work or dimension of energy. In CGS that's why the units again can be written as dyne centimeter. In SI we can write Newton meter. Then we have power, which you may have heard earlier many times, is defined as rate of doing works. So the formula is work by time. So the units is going to be joules per second in SI system and ergs per second in CGS system. So the dimension of power will be dimension of work by dimension of time. Dimension of work is ml square t minus 2. Dimension of time is t. So when this t goes up, it has a power of t to the power minus 1. Minus 2 power minus 1 power is total is going to give you minus 3 power. So we have dimension of power as ml square t minus 3. There are quantities like your angle where we do not measure any mass, do not measure any length, do not measure any time. So angle starts having no dimensions. That's why dimension of angle or any angle that we measure will be equal to m0, l0 and t0. If you remember, we have also a formula for measuring angle, that is your theta equals to length of arc by radius. Notice if you measure length of arc, you are going to measure in meters. Also if you measure radius, you're also going to measure in meters or centimeters. Both the units, they get cancel. So angle will have no fundamental units, and hence I can even say that it doesn't have any dimensions. Next we have something called angular velocity. Now you must have heard about velocity earlier, which is simply displacement by time, which represents how much is the displacement of a given object from point A to point B per unit time. But this time we are talking about angular velocity, which we talk when an object is undergoing motion in a circular path such that the object is here somewhere here right now, then the object reaches somewhere at this point B, such that I can say the object is covering some angle theta in certain time, and that angle covered in a given time is what is known as angular velocity for us. So let me tell you again, how much distance is covered in how much time is known as linear velocity or simply velocity. But suppose you are covering or moving in a circular path and the object goes from point A to point B in the circle, covering an angle of, let's say, pi by 6 radians per second, that is like 30 degrees per second. So your answer becomes pi by 6 radians per second is your angular velocity. We represent this quantity by omega. So we have how much angle is covered in how much time, and angle must be measured in radians. So radians per second is the SI unit of your angular velocity. And then if we want to calculate the dimension, we must have dimension of angle by dimension of time to get the dimension of angular velocity. Now you can see already the angle has no dimensions, so simply we can write m0, l0, t0, which can be simply written as 1, or actually we should not even write this 1 is not a dimension. But then we have your time dimensions, so we must write your t here. So when the t goes up, it looks like t inverse. So this is your dimension of angular velocity. Then we also have something called angular acceleration, which is defined as change in velocity, but this time angular velocity, by time. That means how much is the change in angular velocity and how much is the time taken by it. So it is rate of change of angular velocity. Now change of angular velocity is measured in radians per second and time is measured in seconds. That's why we have radians per second square as the SI unit of your angular acceleration. If you remember, your normal acceleration is given by meters per second square, but your angular acceleration is given by radians. Instead of meters, we have angle here. Second, we still have second minus 2. You can check again. If I want to find the dimension of angular acceleration now, I must write the dimension of change of angular velocity, that's your t minus 1, divided by dimension of time, so we have time t. That's why when I write this, it's going to look at t minus 1. This goes up here, again looks like t minus 1, so we get t minus 2 as the dimension of angular acceleration. Then we have something called angular momentum that we again talk in your rotational motion, not in a linear motion. That is defined, not defined, but let's say it has a formula where we have mass times velocity times radius. So the dimension of, so the unit of angular momentum will be unit of mass, which is kg, unit of velocity, that is your meters per second. So let me write meters per second. Final dimension of, unit of radius, that is your meters. So I'm going to write meters. So we get kg meter square second minus 1 as the dimension of angular momentum. This angular momentum is given a symbol L. And acceleration, angular acceleration, I forgot to tell you, it is given by alpha. Next we have dimension of your angular momentum should be given by dimension of mass, dimension of velocity and dimension of radius. Mass you know is m, velocity is lt minus 1 meters per second, radius is simply your distance, so L. So ml square t minus 1 is the dimension of angular momentum. Finally we have two more to discuss right now. Your time period, you will see, is defined as time taken for every one oscillation. That means if a body is oscillating back and forth, the time taken to complete one oscillation is known as time period. It's simply the time, so it has time dimensions. So unit is seconds and the dimension is t, time. You must have seen a pendulum going back and forth, so every pendulum has time period to go back and forth. Also we talk time period in this context. Suppose we have Earth moving around the sun and taking certain time to complete one revolution, that is called time period of the Earth, and that is, we know, is 365 days. So time period is a quantity which we again talk for repetitive motions. You're repeating your motion a certain time, so how much time the motion repeats after is what is known as time period. That's why it has seconds as a unit and t as the dimension. Then we have something called frequency, which is defined as reciprocal of your time period, that is your 1 by time period, denoted by sometimes symbol f or nu, we call it. So we have 1 by time dimensions for that frequency, that is your t inverse, and the unit will be of course 1 by time unit, that is your seconds. 1 by second, that is your second inverse, is also called hertz. We write Hz. So this is just a brief introduction to what is known as your dimensions to us. What I can say about dimension is that dimension represents the type of quantity that we are talking about. If we have dimension of L square, it's like we are talking about a quantity that is like representing your area. If you have dimension of L cube, it's like we are talking about a quantity which represents volume, and so on. If you have dimension of ml t minus 2, that's like talking about a quantity that's like a force. If you have ml square t minus 2, it's like we are talking about a quantity that's like your energy or maybe work, and so on. And the advantage of knowing the dimension is that we can be sure that we can add those quantities which have same dimensions, and we cannot add or subtract those quantities who do not have same dimensions. Finally, another advantage of dimension you saw just now is that if we know the dimension, we can guess the units, or the reverse is also true. Suppose we know the dimension is ml t minus 2, so the unit of force is going to be kg because of this m here. L dimension means length, so we have meters, and t means seconds, so we have minus 2. So this is not the dimension, sorry, but this is the unit of force, and we know we call it 1 newtons. Then again, SI unit of energy also we have seen is kg because we have m here. L square means length square means meter square. T minus 2 means second minus 2. So you can see this, we have also called it joules, and so on. So what you need to do is that you need to remember dimensions of most of them. If you are ever confused about what will be the dimension of a given quantity, try to go back to the definition of that quantity, or at least try to remember the SI unit of that quantity, or any unit. CGS also can do. And knowing the CGS unit or SI unit or the formula can lead you back to the dimensions.